Hello everyone, my name is Nidhi Singh. I am assistant professor in the International School of Pharmacy, that is a part of the Suresh Gyan Vihar University in Jaipur. So today we are going to discuss the topic that is the carboxylic acid and that comes in the pharmaceutical organization first. And in this we are going to discuss about the carboxylic acid derivatives. Let's start. So the main objective of this topic is so here we are going to discuss about what are the carboxyl acid derivatives, and also we are going to study about the physical properties of carboxyl acid. So what are the physical properties of this carboxyl acid derivative? And also we are going to study about the preparation of carboxyl acid derivatives, and that what are the method of preparation for the carboxyl acid derivatives, and this will last from that we are going to know about what is carboxyl acid derivatives and what are the properties of carboxyl acid derivatives, and then but we are going to learn that we are going to learn about the method of preparation of carboxylic acid derivatives. This is how the carboxylic acid derivatives are prepared from the different reagents and by the help of the different catalysts, and what are the properties of this carboxylic acid derivative, that what we are going to what is the physical properties, that what is the states of this carboxylic acid derivatives, what is the boiling point, what is the what are the other properties which are included in the physical properties of the carboxyl acid derivative. So these all things we are going to study in the topic of this today's lecture. So let's start the topic. So firstly, the introduction. So I have already told you that the carboxyl acid, which is the formation of a two functional groups, that is your carbonyl compound, sorry, the carbonyl carbon means the carbonyl part, and secondly, it is the hydroxy part. So by the attachment or the bonding of both of them, the carboxyl part and the carbonyl compound and the hydroxyl compound, so both of them are bonded and there is a formation of a new function group, that is the carboxyl acid function group. So here from this carboxyl acid function group, there are the derivatives. The derivatives are found from these carboxyl acid, from this carboxyl acid. So how they are formed? So the most important functional group, the most important functional group of the carboxylic acid derivatives of this carboxylic acid are acyl are the acyl chloride, acid anhydride, esters, and there are and R, where R and R dash may be same, and amides, which are obtained by the replacement of OH part of carboxyl group by ClOCO3, OCOR, OR dash, or NH2 group respectively. So in the carboxyl acid part, from this carboxyl acid, we can obtain the functional derivatives of this carboxyl acid. So the functional derivatives of these carboxyl acids are acyl chloride, acid anhydride, esters. In the ester, the formula is your or RCOO dash, where R and R dash may be same, and amides which are obtained. So these function derivatives of this carboxylic acids can be obtained, which are obtained by the replacement of these from the function group carboxylic acid. The OH is replaced by this OH part of the carboxyl group is replaced by the Cl, OCOR, OR dash, ONH2 group respectively. So in this case, they are replaced by this, this OH is replaced by the Cl. So if in the first, if the OH is replaced by the Cl, then it is known as your acid chloride. And if the OH is replaced by the ethyloxy, then it is acid anhydride. And if the OH is replaced by the alloxy, then it is your ester. And when the OH is replaced by the NH2, then your amide. So like this, these these function derivatives of carboxyl acids are formed from the carboxyl acid. From the carboxyl, this xylic part is xyl part means oxyl part is removed from here, and there is a formation of different derivatives of this carboxyl acid. So from here, the most important functional group derivatives of carboxylic acid are your acyl chloride, acid anhydride, esters, esters, amides, and then these are obtained by the replacement of your OH part of function of carboxyl group of acids by Cl, OCOR, OR, or NH2 group respectively. So here you can see from this carboxylic acid, this OH is replaced by Cl, then there is the formation of this acid chloride. When OH is replaced by ethyl oxy group, then there is a formation of this acid anhydride. And when OH is replaced by the alloxy part, then there is a formation of this ester. And when OH is replaced by this NH2 part, then there is a formation of this amide is formed. Next is the physical properties. So what are the properties of this acyl chloride? In this case, the acyl chloride, the lower members are colorless, volatile liquids having irritating smell. Higher membranes are colorless liquids. The boiling points of acid derivatives are lower than that of carboxylic acid due to the absence of intermolecular hydrogen bonding, and they also fume in moist air. So in case of acyl chloride, the physical properties of this carboxylic acid derivatives. So in the first case, that is the acyl chloride. So in the acyl chloride, so the lower member are colorless. So the lower member of this acyl chloride are colorless, volatile liquids having irritating smell. The lower number means the which are attached to the lower number of hydrocarbon chain, that is your CH3. So if that chain is more and more alkyl groups are attached, then more hydrocarbons are attached, then the higher members, they are called the higher members, and the higher members are colorless liquids. So the lower member as well as the higher members are colorless liquids, but the lower members are your volatile liquids, and they are having an irritating smell. So these lower members are having the irritating smell, and the boiling point of acid derivatives are lower than that of carboxyl acid. So the boiling point of this acid derivatives are lower than that of the carboxyl acid due to the absence of intermolecular hydrogen bonding. So their boiling point is lower because the carboxyl acid is there because there is no intermolecular carboxyl hydrogen bonding. So they also fume in moist air. So if the carboxyl acids, they are these acid derivatives having the lower boiling point than the carboxyl acid. It is because due to the intermolecular hydrogen bonding. So in the carboxyl acid, they are having the carbonyl part and the oxygen carbonyl part as well as the hydroxyl group. So the hydroxyl group that is present on this carboxyl acid that is involved in the intermolecular hydrogen bonding. And but in case of this acid derivative, there is or acyl chloride, there is no intermolecular hydrogen bonding because there is no presence of this OH group, or there is no presence, and there is the only presence of this chlorine. So they also fume in moist air. So these acyl chlorides, they are fumed in the moist air. So in this case, with acyl chloride, the lower members of this acyl chlorides are colorless, volatile liquids. They are having the irritating smell, and the higher numbers are colorless liquids, and they are the boiling point of acid derivatives are lower than that of the carboxyl acids, and this is due to the absence of intermolecular hydrogen bonding, and they also fuse in the moist air. Next is the acid anhydride. In the case of acid anhydride, the acid anhydrides are colorless liquids or solids uh, with irritating smell, and they are soluble in organic solvent, although the lower members are readily soluble in water. They have higher boiling point than parent acid due to their larger size. So here the acid anhydrides. So the acid anhydrides are colorless liquids, and they colorless. It can be a colorless liquid or solid. They are also having the same irritating smell like the acyl chloride. So the acyl chlorides are also having the irritating smell, but the difference is that they are also present. Both of them are present in a colorless liquid, but they are also present in colorless solid, acid and hydride, and they are soluble in organic solvent. So these acid and hydride these are soluble in organic solvent, and although the lower member are readily soluble in water. So the lower members are readily soluble in water, but the higher members are soluble in the organic solvents. So in this case, and they have higher boiling point than parent acid due to their larger size. Because in this case, in the acid anhydride, these are larger. They are having a larger size, and they are having a higher boiling point than the parent acid. So the physical property of first again the acyl chlorides. In this case, the lower member of the acyl chlorides are having colorless, volatile liquids, and they are having irritating smell. And the higher members are colorless liquids, and the boiling point of these and the boiling point of this acid derivatives are lower than that of carboxyl acid, and which is due to the absence of intermolecular hydrogen bonding. In acid chloride, there is no hydrogen bonding is present. Intermolecular hydrogen bonding is present because there is an absence of this hydroxyl part. But in the carboxyl acid, there is intermolecular hydrogen bonding is present because there is a presence of the presence of this hydroxyl part in the carboxyl acid. So there is the presence of the carboxyl, and due to their boiling point is much more greater than that of the boiling point. But in case of acid and hydride are colorless liquids, and these colorless liquids, these are present in colorless liquids or solid, and they are also having the irritating smell. So the irritating smell of the acid and hydride is present in that, and they are soluble in organic solvent as they have these acid and hydrides are soluble in organic solvent, although the lower members are readily soluble in water, but this acid and in case of this acid anhydride, if they are having a small chain of the hydrocarbon, it means they are the lower members, and if they are the high, if they are having a hydrocarbon chain, more hydrocarbon chain is attached to that acid anhydride, then it becomes a higher number. So in the acid anhydride case, these are soluble in the organic solvent, but their lower numbers are readily insoluble. These lower members are readily insoluble in your water, and they have higher boiling point than parent acid due to their larger size. So their boiling point is higher. But in case of your acid derivative, they are having lower than the carboxyl acid. But in case of this acid anhydride, they are having the higher boiling point, and because of their uh, larger size, because their size is larger, that is why they are having the higher boiling point. So there next is your esters of acid. So in the esters of acid, these are colorless liquids or solids having fruity or florid odor, and their lower molecular weight esters are soluble in water. So in this case, the esters are colorless liquids or solids, but they are the smell of their is fruity or flowery odor. But in case of acyl chloride and acid anhydride, their smell is irritating smell. But in case of these esters, they are having a fruity or flowy flowery odor. And these are colorless liquids. These esters of an acid is a colorless liquid, and these colorless liquid or solids, and these are having a fruity or flowery smell. And the lower molecular weight esters are soluble in water, and the solubility of ester decreases with increase in the molecular weight. So these are also soluble in water, but the lower numbers means which are having the lower molecular weight. So the lower molecular weight esters are soluble in water. So in this case, they are soluble in water, and they are having the high but the solubility is decreases. Means the solubility is decreasing as the molecular weight is increasing. So the solubility of ester is decreasing. So the solubility of ester is decreasing as there is an increase in the molecular weight. So the esters are colorless liquids or solids. We are having fruity or the flowery odor, and the lower molecular weight. The lower molecular weight is are soluble in your water. These are soluble in the water, but the solubility of ester is decreases. The solubility of ester is decreases. There's increase in the molecular weight. So here the solubility of ester is decreasing with the increase in the molecular weight. So all esters are soluble. So all esters are soluble in all esters are soluble in organic solvents like benzene, ethers, etc. So in this case, the esters are colorless liquids or solids. These are having the fruity. These are having the fruity smell. These are having the fruity or flowery odor, and the lower molecular weight esters, the lower molecular weight esters are soluble in water, and the solubility of esters decreases with increasing in the molecular weight. And the all esters are soluble in organic solvents like benzene and ether. So due to their low molecular weight, they are soluble in water, but the solubility of esters decreases with the increase in the molecular weight. And all esters are soluble in the organic solvents like the benzene and the ethers. And esters also do not form hydrogen bonding. So they have lower melting and boiling point and corresponding carboxylic acid, and the boiling point of normal chain esters are higher than those of the branched chain isomers. So here the esters are your colorless liquids, and the esters are your colorless liquids and solids which are having fruity or flowery odor, and their solubility, they are soluble in organic solvents, and the lower molecular weight esters are soluble in water, but the higher the solubility of ester decreases as there is an increase in the molecular weight. So if there is an increase in the molecular weight, then there is a solubility of its esters is decreases, and all esters are soluble in organic solvents like benzene esters, like benzene as ethers, etc. And ethers do not form hydrogen bonding. So these ethers are not forming hydrogen bonding. Esters are soluble in organic solvents like benzene, ether, etc. So these esters are not forming hydrogen bonding, because in this case also there is the absence of this hydrogen part in this. So so they are also not forming hydrogen bonding with them, and so they have So due to which, due to the absence of the hydrogen bonding, they are having the low molecular weight and the low boiling point. So their molecular weight and the boiling point is lower, and as compared to the carboxylic acid, or as compared to the acids, and the boiling point. So the boiling point of the normal chain is higher, but the boiling point of the normal chain are higher than that those of the branch chain isomer. So in this case, the boiling point of the branch chain, uh, the boiling point of the branch chain isomers are lower than that of the normal chain, which are having the higher boiling point than that of the branched chain isomer. So in their esters of acid, they are having their solubility is in the organic solvent, and they are not forming hydrogen bonding, and due to which there is a boiling and the melting point, um, lower boiling and the melting point than that of the corresponding carboxylic acid, and the boiling point of normal chain esters are higher as compared to the branch chain isomer. Next is the acid amides. So in the case of acid amide, for example, is your except formamide. Except your formamide, which is a liquid. So this formamide is a liquid, and all amides are solids, colorless crystalline solid. So the formamide is your liquid, but all other acid amides are your liquid, colorless crystal solids. These are colorless crystalline solids, and the intermolecular hydrogen bonding. The intermolecular hydrogen bonding is associated in amide, so their melting points are much higher. The melting points are much higher than that of the carboxylic acid, and the lower member of amides homologous series are water soluble. So here the acid amides formamide, except the formamides, that is your HCONH2, that is having which are which are in the state of a liquid, but um, all other amides are colorless crystalline solids, and the intermolecular hydrogen bonding. The intermolecular hydrogen bonding is associated. The intermolecular hydrogen bonding is associated in amides. So their melting point is much higher than that of the parent carboxylic acid, and the lower member of the amide homologous series are water soluble. So in this case, in the acid amides, only the formamide is your present in a liquid state, and all other acid amides are your present in the colorless crystalline solid, and the intermolecular hydrogen bonding. The intermolecular hydrogen bonding is associated with the amide, and so their melting points are much higher. Their melting points are much higher than that of the parent carboxylic acid. So as we compare their intermolecular bonding, so both are having the intermolecular bonding, but the molecular bonding is higher in case of your this acid amide, and in case of the acid amide, the melting due to this intermolecular hydrogen bonding, the melting points are higher than the parent carboxylic acid, and their and lower member. So the lower member of this acid amide are having they are having solubility in water. They are having solubility in water. So the lower members are soluble in water, but the higher number of this acid amides are soluble in the organic solvent. So these are all soluble in the organic solvent, but the lower members of this homologous series are soluble in the water. So they are more soluble in the water, and then due to the intermolecular hydrogen bonding, the melting point is much more larger than the much more larger or much more higher than that of the parent carboxylic acid. That is why the lower member of this homologous series are are water soluble and water soluble in this case. So again, I am discussing the physical properties of this carboxyl acid derivative. So in this case, the acyl chloride, the lower members of this acyl chlorides are colorless, volatile liquids, and they are having an irritating smell. So state of this acyl chloride the state of the acyl chloride are colorless, volatile liquids. These are colorless, volatile liquids, and they are having an irritating smell. So they are having an irritating smell, and the higher members, so their higher members are colorless liquids, and the boiling point of this colorless liquid, this acid derivatives are much more lower than that of this carboxylic acid due to the presence of intermolecular hydrogen bonding. So here there is an absence in acyl chloride, there is an absence of the hydrogen bonding. Um, there is an absence of the intermolecular hydrogen bonding. That is why they are forming fumes in the moist air. So these acyl chlorides are forming fumes in moist air. And next is the acid anhydride. So in case of the acid anhydrides, this acid anhydrides are colorless liquids or solids. They are having an irritating smell. So they are having an irritating smell. They are soluble in organic solvents. They are soluble in organic solvents, although the lower members are readily soluble in water. So there the lower members are readily soluble in water, and they have higher boiling point than parent acid due to their larger size. So these acid anhydrides they are present. The state of matter of this acid anhydrides are colorless liquid, or they can be a solid also. And they are also having an irritating smell like the acyl chloride. And they are soluble in organic solvents. They are soluble in organic solvents. And although lower members, the lower members of this acid anhydride, these are soluble in water, but the higher member of this acid anhydrides, they are soluble in organic solvents. They are soluble in organic solvents, and they are having the higher boiling point than your carboxylic acid. They're having the higher boiling point. So this acid anhydride, they are having a higher boiling point than this um, carboxylic acid due to the larger size. So these are having the larger size. That is why their boiling point is higher than that of the parent acid or your carboxylic acid. Next is the esters of acids. So the ester of acids are present in colorless liquids or solids, but they are having the smell. Order of their is fruity or flowery odor. They are having a fruity or flowery odor, and their molecular weight of this esters of acids are soluble in water. The lower molecular weight, so the compounds that are containing the ester compounds containing lower molecular weight means whose weight is lower, then they are soluble in water, and the solubility of aster decreases with increases the molecular weight. So the solubility of aster is decreases. Here it decreases with increases in the molecular weight. So the esters are soluble in organic solvents like benzene and ether, etc. So the solubility of this ester is decreasing with the increasing in the molecular weight, and they are soluble in all the esters are soluble in organic solvents, and like your benzenes and ethers, and the esters do not form hydrogen bonding. So these esters are not forming hydrogen bonding. So they have lower melting point and the boiling point. So they are not forming, these esters are not forming in the hydrogen bonding. That is why their molecular weight is lower. So there also, that is why their melting point is lower, and boiling point is also lower, as compared to the carboxylic acid, as compared to the corresponding carboxylic acid, and the boiling point of this normal chain esters and the boiling point of the normal chain ester are higher. Boiling point chain are higher than that of the branched chain isomers. So next is the acid amide, and the acid amides except the formamide, that is a HCO and H2, means they are having the one carbon atom, that is why their name is formamide. So in this case, they are having a these are only these formamides are only liquids, and the other acetamides are solids, solid crystalline color, less crystalline solid. So here the intermolecular hydrogen bonding. So the intermolecular hydrogen bonding is associated. The intermolecular hydrogen bonding is associated with amide. So their melting points are much higher than parent carboxylic acid. So there the intermolecular hydrogen bonding is associated in amide. So their melting points are much higher than parent carboxylic acid, and the lower member of these amide homologous series are water soluble. So here the lower member of this amide acid amide homologous series are water soluble. Next is your preparation of carboxylic acid derivative. So first is the acyl chloride. So the acid chlorides are also known as acyl chloride, have the general formula RCOCl, and they are obtained by the replacement of a OH group by a single atom, and they can be formed by heating carboxylic acid as their salts with phosphoric trichloride, phosphorus pentachloride, and the thionyl chloride. So in this, the acyl chlorides are also known as your acid chlorides, and they are having a general formula, that is the RCOCl. RCOCl is the general formula of this acid chloride, and they are obtained, these acid chlorides are obtained by the replacement of OH by the Cl and atom, and they can be formed. So this acid chlorides can be formed by the heating of carboxylic acid, by the heating carboxylic acid or their salt with phosphorus trichloride, by phosphorus trichloride, phosphorus pentachloride, and the thionyl chloride. So these are obtained by heating the carboxylic acid or their salt. If we heat the carboxylic acid and their salt with this phosphorus pentachloride and the phosphorus trichloride, then there is a formation of this acyl chloride is formed. And from acid, the first reaction from acid is that acyl chlorides are prepared by heating in carboxylic acid with phosphorus trichloride, phosphorus pentachloride, or thionyl chloride. So here in this, the acetic acid, that is the carboxylic acid, is reacted with the PCl3, that is a phosphorus pentachloride, and acetyl chloride plus H3Br, that is a phosphoric acid, is formed here, plus HCl is formed here. Next is your acetic acid is reacted with this PCl5, that is your phosphorus pentachloride, and there is the formation of this acetyl chloride plus POCl3 plus HCl is formed. So here in the next reaction, the acetic acid is reacted with SOCl2, and there is a formation of this acyl chloride plus SO2 plus HCl. So from acid acyl chloride, the acyl chlorides are also known as your acid chloride, and these are having general formula, that is your RCOCl, and these can be obtained by heating the carboxylic acid with your phosphorus pentachloride, phosphorus trichloride, or the thionyl chloride, and these are formed by the replacement of the OH group by the Cl group. So here the first reaction of this is the acid reaction. From the acid, how from the acid these carboxylic acid derivatives are formed. So in the first reaction, this carboxylic acid are heated in the presence of your phosphorus trichloride, phosphorus pentachloride, of thionyl chloride. So here PCl3, PCl5 or SOCl2. So there is a formation of this acetic acid is reacted with the PCl3. So there is a formation of this acetyl chloride plus H3PO3, H3PO3 plus HCl. So next is your acetic acid, that is the CH3COOH, and plus PCl5, that is your phosphorus pentachloride, and this is the formation of this acetyl chloride. So in this case also the acetyl chloride is formed plus your HPOCl3 plus HCl is formed. Next is your acetic acid with SO2, SOCl2. SOCl2 is a thionyl chloride, and there is a formation of this acetyl chloride plus SO2 plus HCl is formed here. Next is your this benzoic acid. So here in the benzoic acid, and this benzoic acid is reacted with this PCl3, there is a formation of this benzoyl chloride. So from here, this PCl3, there is a removal of this chlorine, and there is the addition of this OH from this benzoic acid, and there is a formation of this benzoyl chloride. Next is your benzoic acid. When this benzoic acid is reacted with this PCl5, then there is a formation of this benzoyl chloride, which is your acid chloride, and there is a formation of POCl3 plus HCl. So here from here the chlorine is getting attached with the or this CO part, and this OH is removed from here, and it is from here POCl3. Sorry, this OH. This from this OH, this H will react with this one of these Cl, and there's a formation of this HCl, and O will react with this phosphorus, and there's a formation of this POCl3. Next is your benzoic acid. So the benzoic acid is reacting with the thionyl chloride, and with the thionyl chloride, there is a formation of this benzoyl chloride. So this benzoic acid is reacted with the thionyl chloride, and there is a formation of the benzoyl chloride. So this benzoic acid is reacted with this SOCl2, and there is a formation of this benzoyl chloride plus SO2 plus HCl. So here benzoic acid that is having a OH, and this SOCl2, one HCl will remove with this, and there is a attachment, or there is a formation of bond between this P and this Cl, and from here this H will react with one of the Cl, and there is a formation of HCl plus sulfur dioxide is formed here, that is the SO2 is formed here. Next is there from salt. So there are the two reactions, the two method of formation of this acyl chloride, one from the carboxylic acid, and the other from the reaction of this formed from the salt of the carboxylic acid. So this acyl chlorides are prepared by the treatment of sodium salt of carboxylic acid with phosphorus trichloride. So here PCl3 or thionyl chloride. So this sodium acetate, which is reacted, which is treated, which is prepared by the treatment of sodium salt of carboxylic acid with phosphorus trichloride or thionyl chloride. So there is a formation of this acetyl chloride. So there sodium acetate is reacted with this PCl3, and there is a formation of this acetyl chloride plus Na3PO3. Next is your calcium acetate. So now calcium acetate plus SOCl2. So this calcium acetate is reacted with the SOCl2, and there is a formation of this CH3COCl plus CaSO4 is formed here. So from the salt, the acyl chloride, the acyl chlorides are prepared by the treatment of sodium salt of carboxylic acid with phosphorus trichloride or thionine chloride. So here CH3COONA, that is your sodium acetate salt, plus PCl3, there is a formation of this acetyl chloride plus Na3PO3 is formed here. So here the sodium acetate is reacted with this phosphorus trichloride and there is a formation of this acetyl chloride plus sodium phosphate is formed here. And here the calcium acetate, which is also a salt of an calcium carboxylic acid, this is reacted with this SOCl2, that is a thionine chloride, and there is a formation of this acetyl chloride plus calcium sulfate. Next is your acid anhydride. So in case of acid anhydride are formed by the dehydration of carboxylic acid and they are obtained by the elimination of one water molecule from the two molecules of monocarboxylic acid, and the ethanoic anhydride is the most common acid anhydride. They can be produced or they can be prepared by the following chemical methods. So this acid anhydride are formed by the dehydration. Means there is an hydration. Dehydration means there is a removal of the water molecule from this carboxylic acid, and they are obtained. These are obtained by the elimination. So these are obtained by the elimination of one water molecule. So these are obtained by the elimination of one water molecule from the two molecules of monocarboxylic acid. So one water molecule is removed or is eliminated from these two molecules of the monocarboxylic acid. So from that, there is a formation of this ethanoic anhydride, and from this ethanoic anhydride, which is the most common acid anhydride. These are the most common acid anhydride of this acid anhydride, and they can be prepared by the following general method. So this acid anhydrides can be prepared by the following general method, and the dehydration of anhydrous acid and the dehydration of anhydrous acid and acid anhydride can be obtained by heating anhydrous acid in presence of dehydrating agent like phosphorus pentaoxide. So here the acid anhydride is obtained from the dehydration of anhydrous acid. So this acid anhydride can be obtained by heating anhydrous acids, by heating the anhydrous acids in the presence of an dehydrating agent, and the dehydrating agent is your P2O5, that is your phosphorus pentachloride. So here, this acid, here you can see here RCOOH, it is the monocarboxylic acid, and here we have taken two molecules of monocarboxylic acid, and it is reacted in the presence of P2O5, that is your dehydrating agent. Phosphorus pentachloride is a dehydrating agent, and if we heat it in the presence of this phosphorus pentachloride, there is a formation of this acid anhydride, and there is a removal of water molecules from it. Next is your here the reaction is shown that the acidic anhydride is formed, or your ethanoic anhydride is formed here. Next is my heating acid chloride with anhydrous salts of acid. So here acid anhydrides can be prepared by heating an acid chloride with anhydrous sodium salts of a carboxylic acid. So this acid chloride, the sodium acetate are heated, and there is a formation of this acid anhydride plus NaCl is formed here. So by heating acid chloride with anhydrous salts of acid, an acid anhydride can be prepared by heating an acid chloride with anhydrous sodium salt of a carboxylic acid. With the acid chloride plus sodium acetate, they are heated, and there is a formation of acetic anhydride plus NaCl. So by heating sodium salts of carboxylic acid with anhydride, with acetic anhydride. So here you can see that anhydrides of higher acid can be obtained by heating sodium salts of carboxylic acid with acetic anhydride. There is a formation of this acid anhydride plus acetic acid. Next, by the reaction of excess amount of anhydrous sodium salt of acid with phosphorus oxychloride or thionyl chloride. So here you can see that acetic anhydrides are synthesized by treating the sodium salts of carboxylic acid with POCl3 and SOCl3. So here acid chloride is reacted with the sodium salt of acid. There is a formation of this acetic anhydride, and there is a sodium salt of this acid that is reacted with this SOCl2, that is thionyl chloride, gives the formation of this acid anhydride. SO2 plus 2 NaCl is formed here. Next is the esters of acid. So esters of carboxylic acid derivative, which are formed by the replacement of hydroxyl penthoxy H group and alloxy group. We are formed H2 in cellular plant, that is cellular class, and these esters are formed by the general formula by the direct esterification and by the action of alcohol of acid chloride or anhydride. Next is the question. So the first question is anhydrides can be converted into ester by the reaction with alcohol. Reduction of acetyl chloride with palladium barium sulfate will produce the acetyl aldehyde. Next, on reduction of lithium aluminum hydride, acetic anhydride produces alcohol. So on reaction with thionyl chloride, acid chloride is produced. When propanoic acid is treated with aqueous sodium carbonate, the COCO2 comes from this bicarbonate group, and the benzoyl chloride is prepared from benzoic acid by SOCl2. So on reaction with ammonia acid chloride form amide, and acetamide is treated separately with the following reaction, and there is a NaOH plus B atom. And these are the references from where you can study this topic. And thank you so much for today's lecture.